So we're now day 5. 5 days counting down. We have Wednesday, Friday, and then we have the 3 days next week. Goal is we're going to finish talking about relationship of compounds and what's known as chiral properties. So we're going to dive into that part today. This is basically contextualizing why we've been talking about stereoisomers. Yes? Sorry, say that one more time? Oh, midterm 2 grading, we had to do it all as one big team on Monday evening. That's completed now, so I think they're just assembling the grades for that part of it. The videos for how to walk through it will be up by Friday, but you should have your marks back. Again, no promises, but Friday should be when you should have it by. But they're all graded through and stuff for that part now. Okay, as we walk through this, remember, first we were talking about how to identify molecules in terms of what we called either constitutional isomers, conformers, and we've moved over to stereoisomers. Under stereoisomers, we have the two basic new nomenclatures. We have E and Z, which are for alkenes. We have R and S, which are for asymmetric stereocenters, centers with 4 different priority groups. So, the way that the list is broken out is it's meant to go down in priority in terms of what is more or less similar, starting at the top. If 2 molecules have completely different formula, no relation. They are just molecules. Constitutional isomers are the next most similar, right? These are saying that they have the same formula, very different connectivity, totally different IUPAC names. They're not even the same category to each other. One might be an alcohol, one might be a ketone, but they're very different molecules, only similar. These are very, 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 very distant cousins, right? Identical, these are conformers. These are any geometry or representation of a molecule that you could interconvert either by changing how you look at the molecule or rotating sigma bonds. No bonds must be broken. This is only just different presentations of the same molecule. This is cyclohexane geometries. This is conformers like staggered or eclipsing. Once we get over here, stereoisomers, this is where we still need to change bonds. We have a special name for that. This is our E and Z or R and S. We also say that these guys, why they're so similar is because it's just small changes in 3-dimensional presentation. Where the alcohol is, where these functional groups are very similar. IUPAC names are almost identical. The only difference is one might be an E alkene, one is the Z alkene. One might be an R alcohol, the other is the S alcohol. Under the category of stereoisomers, we have these final 2, what we call enantiomers and diastereomers. And again, we're really drilling down to levels of similarity. What we're going to discuss today, enantiomers are so very close. They are nearly identical except for very, very small 3-dimensional point. These are the mirror image kind of relationship molecules. Diastereomers is kind of our bucket for everything that's not an enantiomer. Enantiomers are special. Remember, we left off last time saying that even certain drugs, if you were to dose a pharmaceutical, and if that pharmaceutical was a mixture of enantiomers, everything's the same except for mirror image molecules. Even though geographically looking at it, you might look on paper and go, those are basically the same thing. What a chiral molecule does in a chiral environment is radically different because it is interacting with that environment. So we had this example last time. No relationship, that's just the same, they're just molecules, no formula. Constitutional isomers, they have the same formula, different arrangements. Identical molecules, this is any presentation of the same molecule where you could pick up that picture and make any of the other pictures just by rotating a bond or flipping the molecule around, changing how you view it. It doesn't change the molecule itself. Their IUPAC names are all the same. Similar here, these are also identical. Difference is conformers, again. If we had to name these by IUPAC, they would have identical names. There's nothing that says that the 2 different conformers here have a different IUPAC name. Quick check, left or right? Which is more stable? Right. The right, why? Yeah, diaxial versus diequatorial. Diequatorial is more stable because why? Well, going out, but what's the problem? What are we trying to get away from in axial? What makes it bad? Yeah. Less interaction between bigger atoms. There's a specific term, the di interaction. It is a 1,3 diaxial interaction. So again, you programmed it in. You know that axial is bad. Remember why it is bad. Remember, axial is bad because it's bumping into other axial groups. This is our 1,3 diaxial interaction. It putting these guys into the equatorial plane relieves that diaxial interaction. That's right. If this was an equilibrium, what would the value of KEQ be as written? This is greater than 1, right? Product favored. Good, good. So stereoisomers, these are our closer things. These are siblings. These are brothers, sisters, twins. So under this heading here, we have two special names for our stereoisomers. We break them into category based on levels of similarity. We're going to talk about enantiomers first. Enantiomers, we've kind of addressed this. This is kind of the core definition of what makes these molecules chiral. Now remember, relationships, saying something are enantiomers, this is a comparison between two molecules. This is like saying, what is the familial relationship between you and your sibling, or you and your mom, you and your cousin? It is a relationship issue. Enantiomers, you're saying, what is the relationship between these two? But the things we talked about before, so for example, our butanol here, does it have an asymmetric center? Yep. Is it chiral? Yeah. It has one asymmetric center. Remember, what does it mean to be chiral? Being chiral means it is not superimposable on its mirror image. All we're really saying is, this guy right here, if I created its mirror image, I get a new molecule with a new geometry at its asymmetric center. This molecule is chiral. R-butanol is chiral. S-butanol is chiral. They are enantiomers. So again, I'm trying to specify the property of being chiral, having an asymmetric stereocenter, that is talking about one molecule. Comparing these two, this molecule is chiral, as is this one. They are enantiomers. The relationship between the two is what we're using that terminology for. This is why it gets a little bit mixed, because we said our butanol is chiral because it's not superimposable on his mirror image. Its enantiomer is that mirror image. It's the physical embodiment of the thing that basically made the thing chiral to begin with. Saying a molecule is chiral is the same thing as saying it must have an enantiomer. It may not be on the page. When you're talking about one molecule, if that molecule is chiral, it must exist some mirror image which doesn't look like it. That mirror image is its enantiomer, okay? It's kind of like quantum. In quantum, if you have this sort of plus-minus particle that's both at the same time, spooky at long distance just means these two things are in existence. Having a chiral molecule means there must be an enantiomer, a non-superimposable mirror image somewhere. Now, the one thing that kind of messes people up, look at these two. Do those look like mirror images as they are drawn right now? Not exactly, right? What we're trying to show here is these are mirror images, and this is why asymmetric centers are so, being able to assign them as R and S. If you have the R center of one compound, the other compound, its enantiomer, will have the other geometry. Going through this mirror plane will invert an R center to an S center. Drawing it this way, where the carbon chain is in the same orientation, oxygen is forward, the mirror image, oxygen will be back. You're switching those two centers. All we're really saying is that here, if these two, everybody agree, those are enantiomers, right? They are non-superimposable mirror images to each other because I've placed the mirror plane in between the two. If I were to try and line up parts of it, I will get 3 out of 4, and these two will always be opposite. If I try to line up my blue, black, and green, then the other two are going to be out. These are non-superimposable mirror images. And again, that can be made clear just by orienting it in such a way. Whoop, there we go, sorry. if I choose to orient in such a way where the mirror plane is right perpendicular to the plane of the page, this becomes easy to see. Now, common for organic chemistry is to choose parts of the molecule and line them up such that they are common. In other words, if the green, black, and this yellow or green bond up here, this green bond at the top and the green atom, if those are lined up this way, what you see is forward and back. Along the plane of the page or orienting this way where they have a common axis, they don't immediately look like this left and right mirror image. This is why use your hands is a pretty quick way to do this. If I put my hands this way, I've got a mirror plane between the two. Showing the molecules, as I had in that previous one, we're lining up thumbs and fingers, but as a result of that, palm up, palm down. It's still just a mirror image. It's just you're choosing to take the axis that you're sort of aligning, and we're taking the carbon bond chain, aligning that as common, which gives one forward, one back. This is still a mirror image. You're just using it or presenting it in different directions. So this is common. Showing it this way, we're keeping the carbon chain in a common point. We're aligning the two to really emphasize OH forward, OH back. Those are mirror images. The clue to look for this too, it is chiral if it has asymmetric centers and no internal plane of symmetry. It is an enantiomer if all of the asymmetric centers in the molecule have flipped to the other side. Here we have one asymmetric center that is R. In its enantiomer, that asymmetric center is S. It must be its enantiomer. Okay? These two are enantiomers. Again, they're presented in such a way that the immediate mirror plane, they're not lined up. We're left and right. There's a nice mirror plane. We're doing it again like your hands. Line up your thumbs, line up your fingers. Oxygen is forward, nitrogen is back. In the mirror image, oxygen is back, nitrogen is forward. Once again, we're lining them up left and right this way. Common fingers, common thumbs. But notice again, the geometry at the oxygen center, the geometry at the nitrogen center, both are different. Everything has to change. When you go through the mirror plane, every asymmetric center must change. So here we have two asymmetric centers. One will be R, one will be S, or maybe they're both S. Haven't assigned them. In its mirror plane, they will both be different. Whatever the geometry is here must change, and whatever the geometry here must change. So that's another way to do this, is if you do your R and S notation, you can look at it and say, oh, molecule on the left, that's an SSRSS. On the right, it's the RRSRR, or whatever. So no matter how many asymmetric centers you have, this is how you can work through this property. So first, draw this guy's enantiomer. Okay? Remember, to be an enantiomer means drawing its mirror image. Now you have a choice. As you work through this, you could simply say, I'm going to mentally put a mirror plane, and then I'm going to reflect everything about that mirror plane. So I'm going to choose to draw this in this geometry, where I'm going to put carbon 1 here and carbon 4 over there. Again, this is not the IUPAC naming. I'm just numbering them according to where I put my mirror plane to try and orient the two. If that's how I've done this, then it's pretty easy to fill in the parts. This will still be down OH. This will be up chloro. That's if I've presented the mirror plane there. That's looking at your hands left and right, thumbs together, fingers together, palms facing one way, back the other. We're putting the mirror plane between the two. That's not the only representation. We could have a mirror plane here and reflecting this way. Or, again, we could actually have a mirror plane in the plane of the page, cutting through the atoms themselves. Any representation will give you this mirror representation. And again, it doesn't matter which one you choose, the same phenomenon in terms of R and S centers will hold. The mirror image of this molecule, no matter how you draw it, will have the asymmetric centers, absolute geometry different. So what that looks like, if I place the mirror plane this way, this is how that representation would look. If I choose to put the mirror plane below it, this is how it would look. If I put the mirror plane in the plane of the page, this is the one that we most common see, because what we've done is we've aligned the carbon centers in a common way. And we're just showing chlorine forward becomes chlorine back becomes oxygen forward. Yes?
What happens if you didn't flip the chlorine, but you flipped those?
Excuse me?
What happens if you didn't flip the chlorine to,
One but not the other, you mean?
like if that's just an accident?
Not an enantiomer anymore. That's what we're coming up to. That's called a diastereomer. Still a stereoisomer, doesn't have the same name. Not all the centers are inverted. That is just a diastereomer. Still a stereoisomer, not a mirror image though.
But you have to like invert everything.
Every single center must be inverted for it to be an enantiomer. That's why enantiomers are special. There's only one, no matter how complicated the molecule is, there's only one perfect mirror image. There may be many, many other stereoisomers, but there's only one mirror image. Yes?
That was my question. If they're all the same molecule, just drawn differently.
If it, like all three of these, blue, gray, red, if you go and assign their IUPAC names, identical. It'll be R at the center. Well, here, let's do the assignment. What's the chirality? Absolute stereochemistry here at this oxygen. 1, 2, 3. Hydrogen is 4, right? The lowest party group is towards you or away from you. Okay, so it's towards you. This looks like 1, 2, 3. It looks like it's rotating that way, right? So what is this? R or S? It looks like it's a S, right? But the lowest is towards you, so it's actually a R center. So this is an R center at the oxygen. If you do that here, it should also be R. Here, R. Here, it's going to be a S. Same thing true at the other side. Whatever the geometry is on that particular one, in its enantiomer, R will become S or S will become R. And they all must change. Yes. As we've reflected each of these, since each of the other ones, blue, gray, red, is a mirror image of the guy in the black, those are just different presentations of the same molecule. Same way to say, right hand is my black, the red. Red is my, here, we'll do it this way. Boop, boop, boop. The way I did it up, the red one is mirror plane this way, 2 hands left and right. The other one is mirror plane this way, top and bottom. And then gray is mirror plane this way, that way. They're all still the same mirror image. They're just different orientations of where you've chosen to do that reflection. There's only two different molecules here. Okay? Again, that's why RS notation is your best friend. It doesn't matter how it's drawn. If you can nail what the RS notation is, you will never be fooled. So what are these? Oops. Turn to the person next to you. Absolutely nail this. I want you guys to crush this one. Convince them of how you came to this assignment. Okay, on 3. 1, 2, 3. Answer is? Okay, we got some C. Ambiguity. Okay. Let's start with the one on the left. What's the highest priority group? Highest priority group, one on the left is? Chlorine, yeah. Let's do that guy over here too. Definitely chlorine. Lowest. That should be easy to pick up too. Hydrogen, right? Lowest is there. What's next? What's number 2? Okay, so this is why we use functional group notation. I am now examining you in an oral exam for your PhD. The one that connect. What the heck do you mean? What's that functional group? Carboxylic acid. That's right. The carboxylic acid will be number 2. Why? It is a carbon. They're both carbons. But that carbon is attached to what 3 atoms? It is attached to oxygen, oxygen, oxygen. Up top is oxygen, hydrogen, hydrogen. This will be 3. So we've got 2 and 3. All right. Now we've reduced it to this way. You have 2 options. Guy on the left, lowest priority group is facing you. It looks what? RS. It looks like it's an S. Since the lowest is facing you, that is a R, right? Okay, so this is definitely R. We have just eliminated that. They're either enantiomers or they're both R. The difficulty with the one you have over here, that is that geometry. Lowest priority group is in the plane of the page, right? Sorry, highest priority group is here. That's number 1, sorry. So, if chlorine is here, number 1, hydrogen is away from me. If I'm standing, and this is a Newman projection of this molecule, what you can think of this as, it's almost like looking at it. I'm trying to set it up like this. If the chlorine, number 1, is here, right or left, where do I put my carboxylic acid? If I was going to look at it this direction, right or left? The right. That's going to be number 2. This is number 3. What's the geometry? RS? R. This is a R. This is also an R. It is a pirate. R, R, R. The same molecule. The other way to help you through this, absolutely, is get your model kit. Once you can orient the 2, the problem with the one that we had, we were looking at it where the lowest priority group is in the page. We're trying to assign it in this sort of geometry. And if you have this and you've said, 1 is going to be my chlorine, 2 coming out of the page is my carboxylic acid, 3 is the alcohol, you're turning and looking at it in this direction. Having the ability to manipulate it with your model kit can help you through all the different gymnastics of this. Okay? So practice that part through. So, by definition, if I change at my asymmetric center, if I change those 2 groups, let's say chlorine and hydrogen, I'm going to swap them. Or the carboxylic acid and the alcohol, if I swap those 2 groups, what happens to the stereocenter? Does R turn to S? Does it remain the same? Or do we destroy chirality? Okay. On 3. 1, 2, 3. Answer is B. That's right. What we mean is, if I'm going to choose to leave the carboxylic acid and the alcohol where they are, I'm going to swap these 2 groups. In other words, what was going forward, that's going to be my chlorine now. Whatever's going back is my hydrogen. This is the expression or definition of being a stereocenter. If swapping any 2 groups changes the configuration, that's how we say that must be a stereocenter. More importantly, this was what? Is that RS as originally drawn? That's R. Over here, 1 is chlorine, 2 is my carboxylic acid, 3 is my alcohol, 4, the lowest priority group is to the back. This is 1, 2, 3. It now is an S center. E will become Z, R will become S if you change any 2 groups, right? Changing 2 groups will invert the absolute geometry of any stereocenter. This happens, the mirror plane though, only happens with R and S. Going through a mirror will change that position because again, this is like your left and right hands. So let me prove that to you. Draw the enantiomer of this guy. And you can do this any number of ways. Practicing this is, again, like redrawing how you do your cyclohexane geometries. Choose a standard method of approach, stick to it. Some people really like doing the left and right hand thing, plane of the page in between. You just do that reflection. Totally fine. Other people like to align the carbons. That's where you have your fingers and thumbs aligned, palms face different directions. Either of those two sort of base standards you can use. Just make sure you adopt one and follow it. So first, if I was going to draw this, where I'm saying I'm putting a mirror right here, what that's going to look like is hydrogen will still be up. This here, what's the geometry of my double bond if I reflect it? So first, when I started off, E or Z? Right here, is this an E or a Z? It's a Z. High priority groups here and here are on the same side. If I plant a mirror down there, does E become Z? If I reflect this here, it's just going to look like that. Achiral centers, things that are not this R and S, the mirror just reflects it back. A chair looks like a chair. Flat things still look like flat things. The geometry here doesn't suddenly invert at this alkene just because you pushed it through a mirror. It's still going to have this shape. The difference is going to be where you put your groups. Bromine is going to be to the front, chlorine is to the back, about this mirror plane. What I should say, though, then is, okay, right here, this is going to be, let me check this. I'm floating under the molecule, bromine, chlorine. I think that's a R center. 1, 2, 3, 4. Does somebody agree with me? If you imagine yourself under the molecule, bromine, chlorine, carbon, that's an R. This here is a Z. For this one, still number 1, still number 2, still number 3, 4 is still in the page. The difference now is the rotation. Bromine, chlorine, carbon, this will be an S. This is still a Z. The alkene being flat, that's just like a chair, an achiral object being reflected. No change. Asymmetric stereocenters will change. Yes? What is Z? Z is the geometry for an alkene. Remember, any alkene where we have highest priority group on the same side, that's a Z alkene, right? So, the point we're trying to emphasize here, the enantiomer of a molecule only affects asymmetric stereocenters. R will become S, S will become R. Alkenes aren't part of that nomenclature. If you choose to draw this differently, if you chose to draw this where instead of drawing is that the mirror plane here, the other common presentation for organic chemistry, I'm going to leave the carbons where they were. If I leave the carbons where they are here, and what I do is I just invert. I'm going to leave the hydrogen here. I'm just going to swap these two groups. So to the front here is my chlorine. To the back is my bromine. These two are the same. Just different orientations. So if you choose to leave the carbons in place and only invert the two centers, or if you choose to do left and right, the mirror, this is like what we just worked through for our other problem. There will both be those same enantiomers. Does anybody want me to draw this in that presentation where you can see it clearly? I'm seeing everybody do the kind of rodeo thing. 1 second. Okay. Nope, nope, not that. Okay. If you want to do this by drawing, here is the method I like to use. Bromine, chlorine. Step one. Step one, get your CIP numbering correct. This allows you to simplify that center, right? It allows you to manipulate easier. So I'm going to redraw this as a tetrahedron where this is 2, this is 1, this is 4, oops, 3, and this is 4. So now I'm just dealing with the tetrahedron and numbers. Number 2, I need to orient it such that this group here needs to be in that position. It's in the plane of the page. I need to rotate it such that it is back in this one. Now what that means is, in your mind, hold on to the other bond, whatever bond is not your number 4. You're going to rotate this bond, so that means 4 is going to rotate over to where 2 is, 2 is going to rotate up here where number 1 is, 1 is going to rotate up over there. So we redraw our tetrahedron. I didn't touch where number 3 is. 4 is now back over here. 2 is going to pop up here. And then number 1 back over there. Now, 1, 2, 3. This is an R. That's where we started off. The manipulation I did is this. You're starting off where number 4, the lowest priority group, is in the plane, as is this carbon. We've got our front. This is number 1. This is number 2. 4 sticking up here. What I'm doing is grabbing it here on number 3, whatever bond is in the plane of the page, and I'm grabbing this and rotating it by 1. Now, number 4 is to the back, and it becomes easier to do that assignment. It's just holding on to whatever their bond was in the plane and doing that simple rotation like that. Okay? So, those are enantiomers. Special thing about enantiomers, there's only ever one enantiomer for any one molecule. There's only one perfect mirror image, okay? That's your sort of mirror twin. Diastereomers is the name we use for all other stereoisomers. Anything that is a stereoisomer but not a perfect mirror image, we call it a diastereomer. So you look at these two, we have 2 asymmetric centers. In the other one, also 2 asymmetric centers. From the name, at the 2 position, we have an alcohol, as we do here. This is the same. One of these 2, at the 2 position here, this must be an S center, so is that. And if you notice, oxygens to the back, oxygens to the back, in the presentation of the ring. The only thing that's different is at the 3 center, oxygen is back, oxygen is forward. This is different. The 3s center becomes 3r. So with respect to our asymmetric centers, if all of them change, they're enantiomers. If anything less than all of them, if only 1, if only 2, if only 3, not all of them, diastereomer. It's just the name we give that's the catch-all for any other stereoisomer. Now that means that, again, every molecule will only ever have one enantiomer. Molecules can have a lot of diastereomers, though, depending on how many stereoisomer centers or asymmetric centers you have. So look at this guy. Let's play the game. What changed? Say that again? So this is the game of functional groups. Direct me to where it is on here based on that functional group. Where is it? Right below the ester? That's good. Okay, so yeah, if you have to talk this through, first of all, how many rings do you see in this molecule? Focus on only one. There's 3 rings. Okay, how do you get my eye to go to one of the ring that we're trying to draw me to? What makes the ring at the top very different than the ones at the bottom? What's a functional group hanging off it that's missing at the bottom? Well, there's kind of both esters, right? They both have an ester. Yeah, there's an alcohol up there. No alcohols hanging out down here. So first thing I would say is go to the ring without the alcohol, with the what? What's in that ring that's missing at the top? We've got double bonds, alkenes. So I'm going to focus on the ring with the alkenes. Cool, so I'm down here. Now, alkene on the left, if we go up, what's different at that carbon? At this center right here, we've got, yeah, one geometry is back, one is forward. What about this center? This is the ester attached to the other ring, also different. Did all of the stereocenters change though? Are there more asymmetric centers in this molecule? And some are the same, right? The alcohol at the top, that is definitely, this is an asymmetric center, did not change. This is an asymmetric center, did not change. It's only 1, 2. So these are diastereomers to each other. They're not perfect mirror images. If I wanted to draw the enantiomer of lovastatin, every asymmetric center, if it was a wedge, it's now a dash. If it was a dash, it's now a wedge. If you've only changed 1 or 2, diastereomer. So yeah, lots of molecules have lots of diastereomers. The difference, though, comes down to specifics. Now, does that sort of hit? Again, nice thing about diastereomers, it's just the catch-all for everything else. Enantiomers is the one you have to be careful on because it is this perfect mirror image point. Presentation, geometry, conformation, how you look at it. Don't let that trip you up. So what are these two? Enantiomers, diastereomers, same molecule. So first, let's start at the top. Are they even isomers? Same formula? Yeah. I agree. They're closer than that. They're not just molecules, they're isomers. Okay, are they constitutional isomers or are they better? Constitutional, we've got chlorine, bromine, we've got an alkene, so is that. They're better than constitutional. There's only a couple differences. What about we have two kinds of stereocenters here, right? We have EZ stereocenters and we have RS stereocenters. The reason I can break those into is EZ are these two, right? That's what defines the geometry around the ring. RS, these have 4 different priority groups. So we have an asymmetric stereocenter and we also have 2 other just normal stereocenters. Are they mirror images to each other? Yeah. Are they? No. You got a weird mirror if that's true. If they're not mirror images, what are they? They're just diastereomers. It doesn't matter what the geometry at blue is. If the double bond, if one of them's a Z, the other one's an E, they could never be mirror images. They're not enantiomers. This is one of the nice things about how we call EZ geometries. Since there's no way that this is a mirror image to this, they have to be diastereomers. Oh, man. Whew. They're not mirror images. And that's the thing that'll kill it. It has to be a mirror image to be an enantiomer. And again, we've been focusing only on that RS. You can do the assignment. That's true. As it works out, did the RS change here? Yes. Yeah, right? That's great, but so did the double bond. If the double bond geometry changes, these are not mirror images. They are not enantiomers. They're just diastereomers to each other. So that goes back to the other one we just said. This is not the mirror image that we drew previously. The double bond geometry has changed. So again, diastereomers is the catch-all for all stereoisomers, including just alkenes. Normal alkenes. Remember, just a simple alkene. Is this E or is this Z? Z. Right? So EZ, that's the specification or orientation we can apply to a stereoisomer. Saying that it's Z tells you which stereoisomer this molecule is. Is it chiral? Asking is it chiral is asking two things. One, does it have a non-superimposable mirror image? The other way, does it have asymmetric centers? Any asymmetric centers? Doesn't have a chance. Not chiral. Does it have a stereoisomer? Could I draw another way of arranging these that gives me a new IUPAC name? Yeah, it would look like that, right? So what are these to each other? These are, they're stereoisomers, but more importantly, we give them the special name we just learned is they're diastereomers. They're not superimposed, they're not just mirror images. They are stereoisomers, they're not mirror image stereoisomers, diastereomers. So my point is, that's where we get to this point here. Enantiomers, especially, the only thing that makes them different is this perfect mirror image. They get this special other name called optical isomers because they have this optical quality to them. What they do is they actually influence light. Diastereomers is the catch-all for anything. They don't have to be chiral to be diastereomers. They just have to be stereoisomers. Enantiomers have this special other property. So quickly, this is sort of the rubric or the sort of, if you guys like using either flowcharts or algorithms, you can work through this. Start at the top. Look at the molecule. Do they have the same formula? If the answer is no, you're done. These are just molecules. They're not isomers. If they're yes, next thing you ask is you're basically in this category. They could be identical molecules or they're isomers. That's what you're down to. Do they have the same connectivity? Are all the atoms in the same place? Is it chlorine on one side and then the other one's a ring? If they have the same connectivity, if they have completely different connectivity, they're constitutional isomers. Same connectivity, we are now in the camp of stereoisomers. These guys are close to each other. Once we're stereoisomers, we need to make a decision. Are they mirror images to each other? The other way of asking that is, if they have asymmetric centers, RS centers, do all the R centers become S? Do all the S centers become R? And remember, I'm not saying that there happens to be an R and S in there. The same center. The 2-alcohol must be R in one case, S in the other. If they are not mirror images, if one has an alkene that's an E, one is a Z, they're just diastereomers. If there's 3 asymmetric centers, one R, 2S, the other one's all S, they're not mirror images. They're just diastereomers. If they kind of look mirror images, and this is a visual thing too, this is like what we talked about last time. Remember, they have asymmetric centers. We can assign them as R and S. You're over here. The one last thing you have to remember, are they superimposable? This is where you're saying, if I reflected them, if I draw those 2 mirror images, is there a way that I can overlap the 2? This is that final catch-all for meso compounds. If they are superimposable, you get down to this level, they're the same thing. They're just either drawn differently or they're meso compounds. If not, they're enantiomers. What I mean by this last category here, the one that catches a lot of people is this one. I have this guy, chlorine, chlorine, and I'm asking, what does he look like? What's his mirror image? Okay, the mirror image. One way to do this, remember, if I line up everything, the mirror image could look like this. That's one way to express the mirror image of this molecule. And if it's starting to look like this, based on what we just talked about, this is starting to look very much like enantiomers, right? Oh, chlorine's up, chlorine's down, chlorine's up, chlorine's down. This looks a lot like an enantiomer. We're in that back corner. These 2 molecules, same formula, same presentation, better than constitutional, look like they're stereoisomers. They're not diastereomers. They're kind of mirror images to each other. Good, good. These are the same molecule, though, right? We have this internal plane of symmetry. I could pick up this molecule here. If I were to flip it over, I get the same molecule back. The mirror image I've created is superimposable on the other one. This is a meso compound. As a result, it's also not chiral. So we have this hierarchy we work through. We have each of these inevitabilities and outcomes. Practice. Again, we've got a problem set. built to help you work through each of these different parts and to try to catch you at different pieces here. This takes a little bit of going through, but be systematic. That's the key thing. Rely on your EZ. That's the best way to work through this. So, what are these guys? Do your priority rules. Same formula? I think same formula. Are they closer than same formula? What's going on here versus here? Different connectivity, right? What's that group I circled? I could call that group what kind of functional group or what kind of side chain? That's a methyl. If I had to just isolate, forget this for a second. If I just had to isolate this methyl is on the 2 carbon, this methyl's on the, these guys are what? They're just constitutional isomers, nothing closer. The emphasis I'm trying to put here is just because the molecule looks complicated, do not leap ahead and start doing RS notation. Stop, go slow, look at it from the top down. There's no reason to assign RNS for this compound because they're not even the same. They're just constitutional isomers to each other. What about these guys? Enantiomers, diastereomers, same molecule. Totally different molecule. Okay, you jump to diastereomers. Let's work through it. Same formula? Same connectivity? Okay. Are they mirror images to each other? Why not? Wow, because they're not, right? Bromine is up, bromine is up. Bromine is up, bromine is down. Did all of the centers change? So they are what to each other? They are diastereomers. That's the relationship between the two. Now notice, we talked through this at part 2. Are both of these molecules chiral? They are diastereomers. That's the comparison between two. Are they both chiral? No. Guy on the left is achiral because it's meso. Guy on the right is chiral. Being chiral is the property of one molecule. Diastereomers and enantiomers is a comparison between two. It's a familiar relationship between both. So they are diastereomers. What about these guys? Okay, start from the top. Do they have the same formula? Do they have the same connectivity? Are they mirror images? Yeah, these are mirror images. Okay, we're getting close. Are they superimposable? Could I pick up the guy on the left and flip it over to make the guy on the right? We had some yeses right off the hip. Let's do that. Okay, if I flip this over, it's going to look like that, right? Oxygen was back means up here oxygen is going to be forward. Oxygen is back makes oxygen forward. When they're lined up this way, that's this one here, are they superimposable? So what are these guys? These are, they are enantiomers. Top to bottom, left to right, they're not meso compounds, these are enantiomers. And why is that? There's no plane of symmetry. To get the plane of symmetry, I would have to rotate this bond, right? And if I drew it that way, I could draw this, methyls on the same side. I'm leaving the OH in place. By rotating this one over, I get OH up. By trying to align the two where the two methyl groups are on the same side, so I've got this, what I'm trying to emphasize here is the internal plane of symmetry of the molecule. There is not one here. This is not a meso compound. The conformation where I do that test to see does it have a plane of symmetry in the molecule, no plane. They're chiral. Left and right, they're enantiomers. Again, if you do this strictly by RS notation, you will get the same thing. Assigning this center and this center, one will be RR, the other one will be RS. Okay. What about these two? Again, last one through. Same formula? Same connectivity? Mirror images as drawn? Yeah, they look mirror images. But let's do that last part. What if I took this one, and I'm actually going to flip it over so that I can actually draw it over here, right? So I'm going to put those two. If I do that, oxygen was back, oxygen looks forward. Oxygen is forward, oxygen is back. This is still looking pretty good, right? They do not look like each other. What if I make one more rotation? I'm going to rotate it this way as well, end over end. What I'm going to do here is say, look at this. That center there and that center there are the same. This center here, whoops, let me change that color. Bottom and top. If I rotate it top to bottom, I spin the molecule in its place, then I'm going to get this one is still back, this one's forward. Those are the same thing. Any rotation that you need to do in terms of flipping it top to bottom, rotating it left and right, this requires 2 rotations from its mirror image. I need to flip it over and rotate it top to bottom. So this is where, again, your model kit can help you. The other one that helps you too is it does have a plane of symmetry through here. This is the one where we did that last test. If I were to only rotate this middle bond this way, OH is back. Rotating this bottom one, OH is back. There's my mirror plane, top to bottom. This is a meso compound. Same kind. Okay, guys. We'll pick up on Friday for chiral properties. See you then.